Thank you for joining me this afternoon. We'll be talking about stereographic compilation from unmanned systems. So first, I'm Christian Stallings. I work for McKim-McCreed. I'm the Research and Development Manager at McKim-McCreed. I'm also a certified photogrammetrist, Part 61 pilot, and a Part 107 pilot. I've been working in remote sensing and on the acquisition side for well over a decade at this point. And the gentleman on the right, who's not here, Dr. Orrin Thomas, but he's a very important part of this research, so I think it's important to acknowledge him. Orrin is a senior software engineer at Cardinal Systems. And Orrin and myself, we did this research together. We met about a year and a half ago, and we both have been chasing kind of the same thing, which is to get more out of the imagery that we're getting from unmanned systems. Move this down a little bit, it's a little low. There. So, as everyone knows, I mean, unmanned systems have truly been disruptive in the survey and engineering market. The image-derived point clouds, these bearer types applications, have definitely changed the way we approach earthworks projects like this. We can collect the data very quickly. A lot of times we can get in there and collect all the information in a few minutes to an hour versus having survey crews out there while they have all the machinery and putting people in dangerous places. But with that said, there are some limitations to this approach, the image-derived point clouds. There's things that it does well, collecting bare earth information. There's things that it doesn't do as well. That is, surveyors in the survey industry, things that we want to collect that we can't use this method for. And these are some of those examples we have on the top and the bottom. We have an example of a terrestrial scan and the image-derived point clouds over here. And these are all the same features. So we have the edge of a curb. This is actually a roof vent, a cross on the top of a church, and this is a gutter. And you can see those features are not well represented in the image-derived point cloud. There's not a good way to pull that information out because we're trying to create a derivative of a derivative, and our base product already isn't accurate enough to achieve our goals. So dealing with unmanned systems, we have LIDAR units, we have image-based systems. Obviously, there's a huge price difference between the two. But in both cases, we're dealing with point clouds oftentimes. With the image-based systems, we're using autocorrelation, structure from motion, to get down to a point cloud product that we're then using to create bare earth or give volumetrics, some other information from it. But more or less, we're dealing with either points or pixels for all those applications right now. But in the survey world, this is what we deal with mostly. Not to say we don't use orthos, we don't use point clouds, but when it gets down to it, we want to end up with some kind of vector feature. We want something we can apply topological rules to, attributes, levels, line styles, etc. And that's one of the limitations right now, to get all this information accurately, the edges of buildings, the curbs and gutters. The image-derived point cloud method doesn't work, and doing with ortho for buildings, there can be lean and other things cause horizontal error, and elevations can be incorrect. So Orrin and I wanted to derive a test where we could look at what variables from these less expensive systems, these non-metric drones, were affecting the image quality and what we could control and what we needed to control to get a better stereo solution. And if you're not familiar with stereo, this is where we're looking at two images in 3D, and where we can see the depth. We can put a cursor on the ground and we can vectorize all those different features. So photogrammetry really kind of boils down to two things. You got your EO and your IO. This is your internal orientation, your external orientation. So basically, where's your image in space and what's its orientation, and what's the internal parameters? What's the mathematical model for the distortion of the camera? But all these different variables in a camera are going to affect that. Your flight speed is going to introduce motion blur. Your altitude is going to lower your ground sampling distance. Your shutter speed is going to introduce more motion blur. And if these things are changing as you're flying, that internal orientation model isn't as rigid. It has inaccuracies built into it. So we derived this test where we kind of narrowed it down to kind of a reasonable amount of flights, 22 flights, where we tested different variables. So first we wanted to see what the correlation was for altitude. Then we wanted to see what effect the flight speed has on it. And over here you can see kind of the estimated motion blur based on those things. Then shutter speed, similarly affecting our motion blur. And then this parameter right here, mechanical shutter. So the camera system we were using is a CMOS sensor, but it also has a mechanical shutter. So a lot of cameras don't have a mechanical shutter. It's just electronic. And you get distortion because the sensor is not being captured all at once. It's like a line scanner. So a mechanical shutter helps kind of compensate for this, and it makes some of these errors more irregular, which in this case is actually a good thing. And then we did some oblique flights, and then we also flew with a different drone with a similar camera system. So to do a good test, you need some good control data. So the first thing we did is on our site, we went and used a total station, and we collected 63 trig points. Our closure on that was 1/50,000, so very accurate closure on that. And then to take it one step further, we also took a terrestrial scanner and we scanned this site, because not only do we want information on the ground, we chose this site because it was a church with a very high steeple, so we wanted points that were really close to the aircraft, and then points that were really close to the ground, as well as some of those features we couldn't see, like the power lines. So the scan compared to the terrestrial scan, or excuse me, to the total station, the RMSE on that was 1/100th of a foot. So the two data sets that we're going to use as our control agreed with each other quite well. So as I said, from the terrestrial scan, we extracted additional points that we were going to use to test, to verify this method of stereo compilation. And we picked points that we knew in image-derived point clouds traditionally don't show up well. Some wires, you already saw a profile of the cross, some rooftop features, and things like that. And we extracted 32 points that way. Excuse me, 18 points that way. So this is kind of a layout of the site. It's a pretty small site, but again, we were flying it many, many times. So the red dots represent the 4 points that we held as control. So we still held 4 points, and then the yellow shots are the trig shots on the ground that we tested. The blue shots are those challenge points, and then the green shots are shots on top of the flat roof. So to test this, we were looking at in stereo doing direct measurements. A lot of times in AT you have your control points, and when you're doing your bundle adjustment you also have your checkpoints, and you're testing that within your solution, which we did, but we also wanted to test direct measurements. So we created a tool that would drive us to all these points, and once we got to those points it also shifted us some random error so that the compiler wasn't going directly on the point, just clicking the button. It randomly shifted to cause the compiler to drive back to the point to measure it. And to compare that to the image-derived point cloud, we used LP360, which is a tool I'm sure a lot of you are familiar with, and we just measured the delta Z on those points. So the first variable, ground sampling distance relative to accuracy. So in traditional camera systems, usually there's a strong correlation to what your ground sampling distance is, your pixel resolution, and the accuracy that you can achieve. With unmanned systems, and a lot of the research that's out there, that correlation is very weak with these camera systems, these non-metric systems. So this is one of the things we wanted to test and see how strong of a correlation we had. So this is the same data represented two different ways. So we have it represented in absolute error, and then normalized for the ground sampling distance. And as you can see, the linear correlation when it's normalized for the stereo measurements is the directly measured points was 0.8, which is very high correlation. The photo triangulation measurements, which are the ones within the bundle adjustment, again had a high correlation. And with the exact same data set doing the image-derived point clouds, as you can see, it's got a very weak correlation. So 1's the best correlation you can have, 0 is the worst. The next thing we wanted to check was the shutter mode, the mechanical shutter on versus mechanical shutter off. And I'm sure if you've looked at unmanned systems, it's something that people talk about a lot about these days is systems with mechanical shutter. Well, this is an example of kind of those differences. Again, this is the exact same sensor, exact same camera, the difference being the mechanical shutter was on and the mechanical shutter was off. When you normalize it for the spread, that's 12 times worse than what that spread was with the mechanical shutter on. So of all the things that we tested, this made the biggest difference. The next variable was the flight speed, and the spread on the motion blur from that was around 0.2 pixels up to a little over half a pixel. So that's how much motion blur was in there between those different flight speeds. But interestingly enough, you can see that the correlation was very little. The amount of error that actually introduced was pretty minimal. And then the same with the shutter speed. So we went from as slow as 1/500 to 1/2000, which was the fastest that shutter could go. And again, you see it gets a little better with the faster shutter speed, but again, it's very minimal. So in light of that, you can actually fly pretty fast with quite a range of shutter speed, and of the variables, it's going to have a limited effect on your data. So then the most important part, why we wanted to pursue this in the first place is we want to measure things that are above ground. We want to get the most out of the imagery. We want to extract power lines and rooftop features, tops of signs, things like that, things we know we can't extract from the image-derived point cloud. So we took all those challenge points and we measured them in stereo as well as measuring them from the image-derived point cloud. And you can see the results of the different objects, which are listed down here, from the image-derived point cloud are quite varied. And this is actually meters. So some of these are missing by 11 meters, and all these stereo measurements were hitting around 0.06 of a foot. So the reason is the image-derived point cloud isn't necessarily that bad. We purposely chose features that are not on the ground, features that we know we cannot collect well. The tops of poles, they were never autocorrelated. But it shows that you can still get that stuff from imagery. It's not to say that LIDAR doesn't have its place, but there's a lot of things you can still do with a camera-based system beyond just the image-derived point cloud. So as an example project of where this becomes beneficial, this is just one of many projects we use this approach on now. We still do these rooftop surveys for Tesla. A lot of large box stores are actually putting solar panel installations on them, and they need to know where everything is on that roof. They need to know where all the rooftop units are, the parapet walls, all the existing pipes, the little electrical boxes that run the RT units. So it's important that they have a survey of all this information so they can design where they're going to put their solar panels. So we flew 3 locations in one day. It would have took us 12 total survey days to collect that. After collecting all that data in the field, it took us an additional 6 days to collect all those features. And it may be hard to see, but these are just little 1-inch outside diameter pipes that sit above the roof on little blocks. And we're able to collect all those very accurately. Little tiny electrical boxes for the rooftop units. So we were able to cut our time in half, a little over half, or a little less than half, and our cost savings was significant for that. But the additional benefit of this approach, when we first did this, we did put people on the roof because we wanted verification on top of the roof that the information we were collecting was accurate, since all of our control was on the ground and not on the roof. And indeed it was. And based on our testing, we found that features that are really close to the camera tended to be just as accurate as the features on the ground, actually more accurate, which shows that our internal orientation, our camera model, was holding quite well. So since we did that test, we've actually done a little bit of additional testing. We've worked with Phase 1 with their IXM 100 megapixel camera system, and we've reflown this site. And we're still processing that data, but so far the results are pretty amazing. So the vertical RMSE on that data so far, what we've verified, is 0.029 feet, 0.03 of a foot. So truly survey grade. With our previous testing with the Inspire 2 system with the X4S, we were right there at 0.06, as I mentioned, which is still phenomenal for $5,000 in equipment. With a little more of an investment, Phase 1 camera system, which is actually significantly higher, you get down to survey grade. And the data is phenomenal. At 400 feet, you could see the center of PK nails from where we set all the survey. So the resolution is remarkable. And that's all I got. Sorry, I went through that a little quicker than I thought, but anyone have any questions? Yes, sir.
I wonder if you have any use case to look at linear features, such as maybe utility lines and power lines.
Yeah, so in some of those challenge points, there were points that we pulled out from the terrestrial scan that were actually power lines, distribution lines on the site. So in that graph that showed the challenge points, some of those were power lines. So we went ahead and also extracted some to create a model where we do a 3-point catenary, where we have beginning, middle, end of the line to extract that. But yes, we were able to pull out the lines. From a stereo compiler standpoint, it's a little nauseating because you're looking at these features that are really tiny, that are way above the ground, but we're able to pull them out accurately.
And there's also transformers, poles, and that kind of things. If you need to do some kind of inventory of the electric type of distributed systems, that might be useful.
Yeah, so to fully 3D model it, I mean, we can pull those features out as an asset, but to fully 3D model, it's a little more challenging because you still only have that one perspective. You know, you can't rotate it like you can a point cloud. So there would be some interpretation because you're only looking at part of it, like looking at the top of a pipe and then creating a 3D pipe from that. Can be done, but that might be cost prohibitive, depending on what you needed to pull out. All right. Well, thank you very much.